Okay, so today I'm gonna be solving yesterday Leetcode prom, Leetcode daily. Um, okay, let me close all this and let's go. Was yesterday. Um, Problems yesterday. Okay, so this is the problem that was yesterday in Leetcode daily. Let me remove this crazy solution. So again, like what should be done here is yeah. What should be done here is so there is a binary tree given, and I should find the maximum product of the subtree multiplied by the complement. Like product of the subtree, that means like all the values of the subtree are added up, and then like in this case, so it's gonna be the product of the or like sum of the subtree that has a root at 2 is like 2 plus 4 plus 5, so it's gonna be 11, and then the complement to that is that uh, other part of the tree, so it's going to be the sum of the other part, going to be 1 plus 3 plus 6, and it's going to be 10. So I need to multiply 11 by 10, and that's going to be the weight of this kind of edge. And the weight of the edge is going to be 110, and then I need to find the maximum weight of the edge in this case. So the first idea that I had in my mind is that just so because I can easily calculate the sum of the subtree, the subtree sum with the DFS, and in order like to calculate the complement sum, so for this subtree it's gonna be, let's say, total. I'll have total sum is 21, and say this tree subtree is equal 11, and I can just figure out what the sum of the complement tree is. Just 100, just 21 minus 11 gonna be 10. So if I use my favorite drawing tool here, I will do the following. So let's say um, connect this my drawing pad. That's a little bit harder USB-C. So USB-A is still not that comfortable as USB-C. Okay, that should work. Okay, so this tree, so I have 1, 2, and then 4, and then 5 here, and then on the right side 3 and 6, and then the total sum gonna be 21, and this sum of this subtree gonna be, let's change the color to make it look fancy. So this one sum gonna be sum is equal to 11. So how I can find the sum of this one? I just need to take the total, and so total, so sum of the okay, so this one is equal to total minus subtree, sum of the subtree minus sum. So this, in this case, total is 21 minus 11 is going to be 10. Check if it's equal 10. Yes, of course. 6 plus 3 plus 1 going to be equal 10. And so I need to, first of all, the solution I have, find total 1 plus DFS. And second one, for every subtree, so it's going to be second DFS pass. Calculate sum multiplied by total minus sum. It's called just S. It's gonna be called S. So I'll call this as S, and that one as S. And check it against the result. If the result is lower than this one, S multiplied by total minus S, then update the result. So it's gonna be two passes DFS solution of one of like basically the heights of the binary tree memory, and the time complexity gonna be of n, where n is number of nodes. Yeah, so this is gonna be my solution, and it's gonna be the first solution, solution number one. So here I'll do the following. So I'll do so I'll do the DFS. DFS, I'll call it def DFS, and then I'm gonna accept node as a tree node, and I'm gonna accept result as a list. Let's say assume as list int, and then I'll go and have this, and then I'll return out of there. I'll return integer. So my idea here gonna go call if, so node val plus if node, let's say DFS node left, if node left else 0, and then plus, guess I can do this, plus DFS, and the same for the right node, right, if node right else 0, and then it's gonna return it, and it's gonna be the first step, find the total, gonna be equal, so if root is none, then I'm gonna return 0, or like say, let's say -1, or like int integer infinity, negative infinity. Otherwise, let's say I want to return total, or like just simple case, return -1, and then total is equal DFS node, let's say root, and then I'm gonna have this result is equal empty list, like this. So it can be only positive, so like the values can be only positive. So I'll just return root and then result here. Res here, and then res here. Okay, so it's working at least. So the next one, I gonna check. total equals DFS, and then I'm gonna call it again, and then I'll have this total equals 0, and then I'll gonna check that left is equal this one, and then right gonna be equal this one, and then I'll check if left and right here, plus left plus right, and then if the result 0 is less than left multiplied by total minus left, I'm gonna have res 0. So I'm gonna check just res 0 equal max res 0, and then I'm gonna have this L multiplied by L by total minus L, and then right multiplied by total minus right. And then the first one I'm gonna check the result, and then second one I'm gonna update the result to 0 and then call it again. And now I will be returning breath 0. So this is my solution here. And let me submit. Okay, I'll also have to do this mod. So I'll have this mod is equal 10 to the power of 7, or like 9 plus 7, like this. Let's call it mod capital. Mod. Okay, let's submit and check if it's gonna be successful. Okay, so now more or less successful, and I want to spend my time on other implementations, like again, I can potentially do the following. I can write a separate function. I'm not sure if this max makes sense for the first DFS. I'm gonna have DFS simple, and then gonna be node 3 node, and then I'm gonna return just integer, and then gonna be left and right. As I was doing that, and return node val plus val plus this one, and then plus DFS, call it sum DFS sum, and then I'm not sure if it makes sense because I still need to record this, do this, recalculate the sums. So let me just do this. Plus DFS. Then here let's DFS sum. Something like this. I can even do this optional 3 node, then do if node is none, I'm gonna return 0, and then here I can just do the plus DFS some node left plus DFS some node right, and remove this one. And then the second DFS helper gonna be, I'll copy this one. If node is none, I just gonna return 0, and then the left one gonna be DFS node left. I'm gonna call it like this, and then DFS node right, and then updating the result, and then returning node val plus left and plus right. And then here I'm gonna call it like this, and then call it DFS sum, and then something like this. A little bit more code, but yeah, might be faster. A little bit, but I think that it can be even improved even further. So here I'm doing like 2 passes. So the second alternative for that would be to save the subsums in an array, and then sort the, or like just do a linear search, and do the linear search. So basically on this step, I'm saving all this. I'm doing 1 pass, and like saving all the subsums to the array, and then like I'm doing this, instead of like going again through the tree, I'm going through the list, and then like for every subsum I can get the total, and then yeah, and then I can do the same calculations, but now like spending more time, spending more memory, because I'm gonna have like of, now I'm gonna have of n memory instead of hash memory, or memory complexity. Like space complexity, it's more like space complexity. So here I'll have this array as a list integer, and then I'll go gonna result append this values. Okay, result dot append this values, and then I gonna return result -1. So now I will do the following. I'll do so I have DFS, it's called just DFS, and then I'll have the sums equals like empty array, and then let's call it sums, and sums, and then let's call it DFS for the sums, and then gonna have this total is equal sums the last one, sums -1, and then I can just linearly go to the for sum in sums. I can get the sum multiplied by total minus sum, and then I can return max. Few typos here and there. Let's run it and see how it's gonna go. Oh, actually I need to do again this mod. So this one is, even though it's like, it's using more memory, but like in the time complexity gonna be the same, because like I'm doing the second pass through the list instead of through the tree, and that might be like more optimal memory placement and like all this cache optimization, CPU caching optimizations, and also like here I'm using this mux and then this generator, and I assume in Python it's done through the C bridging. That's why it's like really efficient. That's why it gives me like 90%, 90th percentile for the runtime. So the second one would be, or like not the second one, but if I instead of like doing this linear search, I can do the sort. Like I'm from the I'm moving from the best to the worst. So now I'm like adding the space complexity was initially O of H, where H is height of the tree, and then I moved it to O of N, and the time complexity initially was O of N, and then like for the second solution it was O of N, and now I'm moving that to the O of N log N, because I'm sorting it. So I'll sort the sums array, sort, and then sort sums. And then, so I need to find, so I have access. Say I have access, and this equation y is equal x total minus x, and I have like sorted access. So the this graph gonna be something like this. So it's gonna be parabola. It's gonna cross the. It's gonna be y is equal x minus x squared plus x multiplied by total. So it's gonna be something like this, like this. I don't know, I'm not good at this at drawing parabola. So let's say you have x and y, and we have the first intersection. So the first one, when y is equal 0, is going to be x is equal 0, and the second intersection going to be when x is equal total. So this part going to be 0, and the entire like function going to be 0. So x is equal total. Y is equal 0, and because like there is a negative sign before x squared, means that like this parabola gonna be like look like this, and if it was like positive, it would be like this. So what's the coordinate of the maximum? So the coordinate of the maximum is gonna be total by 2. The problem is that I have access that kind of not evenly distributed, and that's why I cannot just take the middle one. So it might be like excess in the front and then one excess in the end, and I need to figure out which x is the closest to total over 2 value, and that's the closest one. I need to put this x, let's say x dash into the equation and return the result. So it's gonna be the result's gonna be x dash squared minus x dash squared plus x dash multiplied by total.
Can you just invite this later?
Okay, later. So And that's gonna be the maximum actually, and I should return it as an output. So how I can find this x that be really close to total over 2? I can do the binary search because like I can do through the like I can sort the x's, and I can like take the middle one, say middle one gonna be here, and I'm gonna check like, okay, if this middle one is greater or less than total over 2, and if it's greater I go to the left, and if it's less I go to the right. So here I go to the right, and then basically I need to figure out, okay, what's the delta, and then like the closest delta, I should return the closest delta. So what I'll do here, I'll do the sorts for the sums, and then I'll do DFS. Oh no, I'll do just sort for the sums after the DFS, and then I need to do binary search for the so target gonna be total divided by 2. Or 2, and then I'm gonna go and let's say we have a bad index is equal -1 and a good index is equal len sums, and then while bad minus good minus bad is greater than 1, I'll do the following. I'll do middle equals bad plus good minus bad, and then I'll do if this is over 2, and then if sums m is less than target, I'm gonna go and do bad is equal m, else good is equal m, and then in the end I need to check what's gonna be the better one, if it's good or bad. So I'll do return maximum between total, let's say good sums good multiplied by total minus sums good, and then the second one gonna be sums bad, sums bad here. So let's check if it runs. It doesn't matter the order between total and then some sort. So let's check if it's, oh, I need to do mod. I keep forgetting about this mod. Okay, that's one is better, And again, like sorting, not really bad there. I guess it's somewhere in between. This one can be this binary search. Yes, in Python you can do the binary search in Python. So you can do bisect, something like bisect left, bisect right, bisect okay, let me substitute whatever I have here. So I'll do this bisect left for the thumbs, and then target T, and then I'll do the same. Let's say I'll have good equals this one, and then bad one gonna be good -1, then good -1. Let's do this one. Bisect A is not defined. Let's do this one.
Can you go?
Okay, so now it's a little bit better, but yeah, binary search, I guess this one might be there might be like a bridge to C, something like that. Though if I do just if I do this instead of this one, if I do the this one, will it work? Yeah, it won't. Yeah, so that's guess that's better. So I wonder why that wasn't working. So sometimes it might. Oh, okay. It might be insert index, and that it might be like bad. Like it might be like not like maybe something like this. So if I'm searching for, let's say, 100, so let's say I have target equals 100, and then I have the values, let's say 10 and then 1000. And in this case, I will choose 1000 because like the insertion index is gonna be 100. But actually what I need to choose is 10 because it's closer to 100 than 1000 to 100. So 10 is closer to 100, so delta gonna be 90 between 10 and 100, then delta between 1000 and 100. So in order to avoid this situation, I'm checking both good and bad. Good is when the sums good is greater or equal target, and then sums bad is always less than target. So in the case when like there is no equality, there might be like something like this. This one is greater than target, and this one uh, is less than target. And in this case, I need to check both to figure out whichever is like good or bad gonna be closer to target. And like I do this through the indirect. So instead of checking the delta here, I'm checking actually the answer, and like whatever is closer to target will give the higher value for this parabola, like for the function, and that's why I'm just comparing the results and then returning the results. A little bit shortcut. But I guess if you are still with me, it's already which 35th minute, and I have the interesting solution. Somebody told me about this solution, but still I have troubles understanding why it works. So the idea for this solution, is to first update tree to record of sums of subtrees. And then the second one would be do a greedy search for the target. For the target, and the target should be sum over 2. And that's basically it. So the secret sauce is like do this greedy search, and the greedy search will be like O of h, and then the update tree is gonna be O of n. So it's gonna be generally like O of so the time complexity for this one gonna be O of h plus n, or just O of n, and the space complexity in this case is gonna be O of 1, and it's gonna be just one pass. So like it's more like gonna be time complexity gonna be like n plus h, where like n is number of nodes in a tree and h is like number of the heights of the binary tree. So I'll do here the update. I'll have this so I'll have this val is equal. I'll have node dot val is equal node val plus this DFS, and then I'll return node val. And then I'll call the DFS for this one, and then I'll have this the greedy algorithm, how it can be calculated. So I'll have this left node is equal let me remove this one. So I'll do while so I'm recording while so I'm trying to remember what was that solution. So DFS was the root and sums, and now I go for the left from the current, and left gonna be, it's called left node is equal root dot left, and then right node gonna be equal root dot right. So while left and I'm gonna have so the left one while so first of all let's figure out left is equal root dot left root is gonna be, so initially if root is none, I'm gonna return -1 here, and then I'm gonna do the following. So left, no, like left is equal root, let's say call it node dot left multiplied by node dot val. So node dot left dot val multiplied by node val minus node dot left dot val, and then right gonna be node dot right val multiplied by node val minus node right val, and then initially the node gonna be root, and then I'm gonna compare if left is less than right. I need to go let's say right node is equal root dot so I need to have this comparison between so let's say we have like result is equal if result is greater than L maximum L, and then left and right, I'm gonna return the result. And then here I'm gonna have result is equal 0, and then I'll have this while
Another 5 minutes is over.
while node okay. Okay, so like the greedy algorithm update, so I have like node is equal root, and then while node left is not none, and node right is not none, I'm gonna do left, it's gonna be node left val multiplied by node left val minus current node val, and then it's gonna be if node left is not none else 0, and then the same gonna be for the right. So it's gonna be node right multiplied by the node right minus node val. If node right is not none, else 0, and then if left is less than right, I'm gonna go to the right. Let's say if left is greater than right, I'm gonna go to the right part, and then else here, and then I'm gonna check if left is less than rest, I'm gonna return rest, And then here also, if write is less than res, I'm gonna return res. And then what I'll do here, I'll go to the left side node dot val, say updated value for the node dot left dot val is equal node dot val minus node dot left dot val. And then node is equal node dot left. And here I'll have this node right val is equal node right val, then right. And then I gonna have this update for the res. Res is equal L, and then res is equal L here. And then in the end I gonna return -1, something like this. No. So here gonna be just a simple one DFS without extra array. And here be something like this. And this. So I need to maintain just a total with the value. Here, but it's not left value, not that well. Okay, so let's do this print format and then root. Okay, value, no, not really. If not dot left is not none, and else if okay, it's vice versa, not dot wall, because not dot wall has updating total, so it's gonna be not dot wall gonna be always gonna be equal to total. Okay, and here put this -1. Return res. Why don't we return just res? Okay, so and here also I should return mod, and then here I can just do this left greater than right, return res mod, and then here res mod. Yes, I can just call break, and then here just can call break. Submit. Okay, I know why last time limit exceeded because of the print. Yeah, so that's kind of greedy approach. So here DFS, I'm doing one pass for the DFS for the entire tree, updating the tree in place, and basically instead of like values, I'm updating the tree at node value gonna be sum of the subtrees, sum of the values of the subtree when the current node is actually a root. And then I have this greedy algorithm that's gonna have time complexity of h, where h is just a height of the binary tree. So the total time complexity gonna be one pass for the entire tree, and then h of ops for going up to the h length. and like it depends on the also on result. Yeah, that's very kind of. I'm still so like here I'm taking the greedy decision whether I should go to the left and or to the right branch. I still kind of scratching my head and trying to prove it to myself why this condition is enough, why there won't be a bigger product of those two numbers, and say on the right subtree when the current left uh, edge weight is greater than the right, why I won't be able to find a better solution on the right subtree. I should go to the left only. And it's like it's a local decision that affects the result, and because of this one, it's gonna be like really efficient way um, to figure out what the maximum edge weight for the tree, and the edge weight is like this one weight where I just multiply the left subtree sum to the right subtree sum. So that's it. Again, very smart solution. Hope you like it.